So thank you, Jan and IPGP, for organizing this great workshop. I'm sure Paul is very happy from up there to see us all gathered today, these 3 days to discuss his work, right? And everything is started in Tibet. So I picked this topic today for 2 reasons. First, because I went there with Paul in 2002 and 2005. That's the only 2 big field trips I did with him. And also because, as you probably know, there has been this Mw7.1 Tingri Earthquake exactly in that area in southern Tibet. So you can see on this first slide, this very large normal faults that cuts the young alluvial surfaces and also these older terraces. So southern Tibet is located between the Karakoram Fault to the west and the Jali Fault to the east, south of the Bangong-Nujong Suture, or the Karakoram-Jali Fault Zone, like Paul and Rolando Armijo defined like 50 years ago. So I will discuss the Yadong-Gulu Rift here, which is the closest to Lhasa, the well-studied one, and the Xainza Dinggye Rift here. So we want to quantify the late Quaternion extension rates across this 1,000 kilometers region of southern Tibet to understand Tibetan deformation and also to discuss the high plateau evolution during the later stages of the continental collision. So southern Tibet is dissected by 7 main north-south trending grabens. And along the Karakoram-Jali Fault Zone here, you have this right lateral stratigraphic faults. So you have the Xainza Fault here that connects with the Xainza Dinggye Rift. And you have the Bengtso Fault that merges with the Yadong-Gulu Rift here. And the Tingri Earthquake occurred in the southern part of the Xainza Dinggye Rift. So if you look at the historical earthquakes, so along the Yadong-Gulu Rift, you see many, including the large magnitude 8 Yongbajing earthquake in 1411, as well as the Bengtso and Gulu earthquakes, 7.7 and 7.4 in 1951 and 1952. But when you compare with the Xainza Dinggye Rift, there's nothing, okay? You have one in 1934, just north of Xainza, magnitude 7.3, and this year's earthquake here, 7.1. And also one of the particularities of those grabens is that they're bounded by mostly normal faults, but along the Yadong-Gulu Rift, and especially in this zone between the the Gulu Bend here and Yongbajin along the Nianchan-Tangala Range, you have also this left lateral component. And this is my former PhD student who went to his postdoc with Paul afterwards, and who will be in Grenoble with Anne shortly for a year. So this is preliminary data, and he finds a slip rate of 3 millimeters per year, left lateral. So very significant. So then we collected samples at several locations along the northern Yadong-Gulu Rift. So first, this Gulu moraine right here. You see the crest that is cut by 20 or so fault scarps facing up, facing down. You have Paul in one of those small graben, and Jérôme and Liu Xiaohan in 2005. And we have a very, very high extension rate up there. We have a throw rate of 1.8 millimeters per year, and that means an extension rate of 6 millimeters per year. Then the next site, here, the Gulu terraces, we have a throw rate of 6 and an extension rate of 3, so it's decreasing slightly. And then in the Yongbajin, the Damshun corridor right here, we have an extension rate of 1.6. And now if you look at the Yongbajin graben, just north of the Yalong-Tsangpo Suture, we have a site on the western side and a site on the eastern side. And on the western side, you have this moraine that was first spotted by Paul and Rolando in the 80s. You see here, Paul holding the total station to measure, the different offsets. And on the eastern side, we have numerous faults that cut these alluvial fan surfaces and vertically offset them like a staircase topography. So if we combine the rates, the extension rates at these 2 locations, we get about 1.2 millimeters per year. So now if we look south of the Yalong-Tsangpo Suture, along the Yadong Rift, you can see that the rift is not as mature. you see that it consists of these three sub-grabens, and there's also a left lateral component of motion. And you can see even one of the rivers is vertically offset with a waterfall, about 2 meters high, probably showing the last major earthquake. So it's still visible. And you have numerous moraines. This is a 15-meter high scarp. You have this left lateral components here. So the vertical throw is quite uniform along the Yadong Rift at 0.9. The extension rate is uniform at 0.8. And the left lateral slip rate varies between 0.6 and 2.3 millimeters per year. So when we take all of the data at the late Quaternary timescale along these north-south grabens, so you see we have lots of data on the Yadong-Gulu Rift, not just from us, and then one data point from the Western Amadrime Rift, Amadrime Range, and then one from Paul's collaborator, Li Kong. Paul is a co-author, obviously, and then one from the Pulan Rift. And you can see that all of these data regarding throw rates, they're quite uniform between 1 and 2 millimeters per year. So that seems to be the norm in southern Tibet. So what about the extension rates? So when we put all of those data along the Yadong-Gulu Rift, so I presented the ones with the yellow stars, in the south it's uniform at about 0.9 millimeters per year. And then when you pass the Yadong-Tsampo suture, it's averaging at 1.3 millimeters per year. And suddenly, after you pass the Gulu Bend, it increases rapidly to 3 and 6 millimeters per year of extension, which is very large. So we inferred that this sudden rapid northward extension is due to the Benzo fault, which is right lateral strike slip right here. So we inferred that it must be influenced, the extension rate here must be influenced by the Benzo fault. And indeed, this fault moves at about 5 millimeters per year. This is also a paper with Paul and Li Kong. And then we further inferred that if each of the 7 main rifts absorbs 1.3 millimeters per year of extension, which is the average extension we have here, that means that the total east-west extension over 1,000 kilometers is 9 millimeters per year. So this is what Armijo and others find as well. And that corresponds to about half of the current shortening rate across the Himalaya, like we saw yesterday, 15 to 22 millimeters per year. Okay? So now what about the Xainza Rift? Do we also see a sudden rapid increase towards the north? That would be due to the Guerinzo fault, which is also a dextral fault here at the north. That could be, the rate along the Guerinzo fault is not as well constrained. It varies between 1 and 5 millimeters per year. So we don't know. So do we need to refine the total extension rates if that is not the case? So let's see. So we have data in the southern part of the Xainza Dinggye Rift, including right there where the Tingri earthquake happened. So first, let's look at the northern part of the graben. So you have the Guerinzo fault here with the Guerinzo Lake and the 1934 surface rupture that was mapped by Paul and Rolando in the 80s. And then you have the Xainza normal fault here. So we revisited these sites 89 years after the earthquake. And you can see that it's still very, very well preserved. That's quite impressive, actually. So we mapped with the modern tools that we have, with the drones, and we built UAVs, and we took photos of the northernmost terminus of the rupture. You can see a small graben here. And then other parts, we have this beautiful fault scarp that is well preserved. And then we flew the drone over this one particular alluvial fan here, and we measured the vertical offset, co-seismic vertical offset at several locations, and we obtained 0.7 to 1.4 meters, which is what Armijo found by being in the field in the 80s. So all along the northern Xainza Rift, so all along the rift, actually, you have evidence of normal faulting. So you have these very impressive triangular facets, You have offsets in the terrace risers of sediment layers. You have these numerous faults facing east, facing west, and also faults pressing older surfaces such as moraines. So the first site that we have located here is the Jonah fan, which is this fan here that is cut by 3 main fault scarps. The frontal one is 12 meters high. You can see the goats here for scale. And then you have 2 other faults there. But unfortunately, the Xainza Range there, it's not granite, it's volcanic rocks. So it was very difficult to get enough quartz to do the cosmogenic dating, but we still managed to have some samples, some ages. So we flew the drone, we did a high resolution DEM, and then we could measure the total vertical offset across the 3 scarps, and that is 20 meters, okay? And then we dated this fan, and it's much older than what we expected. It's 46,000 years old. So when you match the age with the offset, you get a throw rate, which is much lower than what we have along the Yadong-Gulu rift, right? 0.45. And then we could estimate the dip of the fault from the terrace risers. That means that the extension rate is 0.3 millimeters per year. The second site is the Ayong terraces here, which looks a lot like the Gyekara terraces along the Yongbajing graben. So you have these numerous faults cutting these older terraces and alluvial fans. The one in the front, which is not being refreshed by active alluvial fans at the bottom, is 40 meters high, just one scarp. And it's very steep. We can't climb that. You have to go around. And the smallest offset across the youngest surfaces is 3 meters high. And again, volcanic rocks, so again, a problem of dating. So another view from the drone with the 40 meters high scarp across these youngest surfaces, and further south where you have 10 to 20 fault scarps, but much more subdued. And then we mapped the sites. We have 3 main fans and some alluvial terraces in the river valley. So on the DEM, we could measure the total vertical offset from the oldest surfaces, and this is 75 meters, and across the youngest surfaces, which is 19 meters. And then matching with the ages that are not very well constrained, but it doesn't change anyway, it doesn't matter so much, because the throw rate we obtain is quite slow, right? 0.5 to 0.7 millimeters per year. And for the youngest surfaces, it seems to be a bit higher at 1.3 millimeters per year. Same for the extension rates, since we take the same dip angle. So we have low extension rates for older surfaces and a bit faster extension rate for the youngest surfaces. So we might infer that there's a temporal rate variation with rates for post-last glacial maximum surfaces being faster, maybe due to post-glacial rebound. So what about the southern part of the Xainza Dinggye rift? So most of you have heard of it, right? It happened on January the 7th, 2025, along the Digmutso Lagoy fault, which is located right here, okay, in the southern part of the Xainza Dinggye rift. So many of us have been working in that region for a while, and this is a great opportunity to finally publish these results. So we have Jérôme and Jingliu and others, and my student here working on these. So this is what it looks like. This is the northernmost terminus of the surface rupture. So this is the Lagoy fault, which crosses the Lagoy massif to the north. The rupture is about 20 kilometers long. And this one location is where you have the maximum co-seismic vertical offsets. This is a photo with 2 meters, but the maximum is about 2.5 meters. And this is also where you have about 2 meters of maximum co-seismic horizontal offset. So other photos of secondary cracks farther south along the Dimutso Lake. You have these grabens that are quite deep. And then you also have push-ups, actually, because when you mobilize sediment suddenly, from upstream to downstream, you have extension upstream, then you have compression downstream. And this is a village that got destroyed. And in the background, you can see the fault scarp, cumulative fault scarp of the Dingmutso fan, which I will show in a second. So the Dingmutso fan was first mentioned and studied by Armijo in '86 with his famous paper with Paul. And so we have samples from the upper surfaces of these two fans. The offset is about 22, 24 meters high, cumulative offset. But at the same exact location, you have a co-seismic offset of 80 centimeters right at the base. I don't know if you can see, but this is the cumulative scarp. And you can follow here the co-seismic scarp. So right there. And this is the southernmost part, terminus of the surface rupture of that earthquake. So we had an DM before the earthquake, and of course a DM after the earthquake. And you can see, so we did other profiles on the DM after to see both the co-seismic offset and the cumulative offset. And you can see the 23, 25 meter offsets, and then the 0.8 or 0.3 meter offset. So the age of the fans is 19,000 years old. The offset is 23 meters, so we get a throw rate of 1.1. And then luckily, finally, we have a very precise dip angle for that fault given by the earthquake. And so we can measure, determine the extension rate, which is also 1.1 millimeters per year. So what does that mean? That means that this Dingmutso fault, which is only about 30 kilometers long, it's not minor. It absorbs 12% of the total east-west convergence rate across southern Tibet, which was 9 millimeters per year. So it's quite significant. And then if we combine the co-seismic offset of 80 centimeters with the rate of 1.1, that means that we have a recurrence, an average earthquake recurrence interval of 700 years, which is actually not so long. And then that means that there's so many similar minor faults, or we thought so. We thought they were minor, but that means that we should go to work and study them more because they could all produce like a large earthquake of 7 something. So then what about the southern part of the Xainza Rift across the Ahmad Rim? So this photo with Paul in 2005, then we went back last November. Exactly there again in 2024. You can see less ice, actually. And then we have other sites. We have the Zongtso scarp right here, which is about 12 meters high. It's 6,000 years old. So we have a fast throw rate of 2 millimeters per year, which means extension rate of 1.8 millimeters per year. And this is located here on the eastern side of the Ahmad Rim Horst. Another site that we have nearby, it's the Dinggye South Moraine, which is 20,000 years old. And you can see the fault going along the mountain range. And you can see these beautiful truncated triangular facets. But the problem is that we cannot measure the fault scarp at exactly the location of that moraine because of landslides, rock falls and stuff. So we measured the fault scarp in the 2 valleys on each side of the moraine. And they're similar, they're actually identical. 7 meters here, 7 meters here. So this is this valley here and this valley here. And we have data on the Zongtso fan as well, Zongtso sites. So then what do? So we have 7 meters in the valleys. We can't do anything with the moraine age, but we can assume or infer that those surfaces have a similar age as here. That means that the throw rate would be 1.2 millimeters per year, or the extension rate would be 1 millimeters per year. So I'll just show you this. This is ongoing work. We sampled these very nice this terrace and this moraine, which are clearly vertically offset. You can follow the scarp for quite a while. This is just north of the Yalutsanko suture. So we are waiting for the results. So what is it? Is it behaving in a similar way as the Yadong-Gulu rift? Well, apparently not, right? The rates across the Xainza Dinggye rift are quite slow, at most half of those along the Yadong-Gulu rift. So why would that be? So either you can see that the Xainza fault actually continues past its junction with the Xainza Dinggye rift for quite a while, for another 60 kilometers or so. And you can see the fault. It's not spectacular, but you can see it. But by comparison, the Xainza fault actually merges with the Gulu fault. And that was published by Dick Hong and Paul, that the rupture actually really merges. It doesn't continue past the rift. So that could be one explanation. And also what I briefly mentioned earlier, the rates appear to be lower pre-LGM and faster post-LGM. So maybe we need to look into that actually, into a temporal rate variation. But in any case, the fact that we previously assumed a 1.3 millimeters per year rate on average might not be correct. Maybe only the major rifts, like the Yadong-Gulu rift, maybe the Tonga-Yimso rift, or the Lupongongri, maybe they move faster, they absorb more extension, compared to maybe smaller rifts. That needs to be resolved, because not many late quaternary data. But in any case, what we said with Paul in 2020 is that the extension north of the Bongong-Nujong suture is clearly driven by sinistral extrusion along these large-scale destructive faults, like the Haiyuan and the Xianxue fault. But in the south, it's driven by diversion and Himalayan thrusting at a rate of 9 millimeters per year. And then we later suggested this new model that Anne and others presented already. But basically, the western Qiaotong terrain, it's made of numerous small scattered normal faults that absorb distributed deformation. But to the east, it's clearly more rigid extrusion between the Xianxue fault and the Jiali fault. And you can really see that in GNSS signal. And to the south, the extension is due to diversion orthogonal thrusting along the curved Himalayan arc. And the limit of this extrusion or distributed deformation is given by the Xianxue fault, which connects with the Xianxue fault here. Oops. Yeah. So thank you, Paul, first, for giving me this great topic 20 plus years ago, and for enjoying Beijing life these last couple of years. Thank you all.